There are two objectives in this experiment. The first one is to determine the volume and density of ball bearing, and the second one is to determine the volume and density of glass block. The vernier caliper allows you to measure external thickness, internal diameters, and depth of the hole to a maximum of 130 mm with a 0.05 mm approximation. The vernier calipers found in the laboratory incorporates a main scale and a sliding vernier scale, which allows readings to the nearest 0.02 mm. This instrument may be used to measure outer dimensions of object using the main jaws, inside dimension using the smaller jaws at the top, and depths using the stem. To measure outer dimension of an object, the object is placed between the jaws, which are then moved together until they secure the object. The screw clamp may be tightened to ensure the reading does not change while the scale is being read. The first significant figures are read immediately to the left of the zero of the vernier scale, and the remaining digits are taken as the vernier scale division that lines up to any main scale division. It is best to take each measurement several times and then to compute the arithmetic mean of the value. This is because the sample may only appear to be regular, or it may deform when the caliper put pressure on it. It would be a mistake to ascribe to the value of the measurement in accuracy equal to the caliper sensitivity 0.05 mm. A better estimate of the measurement error can be obtained by taking the difference between the minimum and the maximum measured value. The micrometer screw gauge is used to measure even smaller dimensions than the vernier calipers. The micrometer screw gauge also uses an auxiliary scale measuring hundredths of a millimeter, which is marked on a rotary thimble. Basically, it is a screw with an accurately constant pitch, the amount by which the thimble moves forward or backward for one complete revolution. The micrometers in our laboratory have a pitch of 0.50 mm. Two full turns are required to close the jaw by 1 mm. The rotating thimble is subdivided into 50 equal divisions. The thimble passes through a frame that carries a millimeter scale graduated to 0.5 mm. The jaws can be adjusted by rotating the thimble using the small ratchet knob. This includes the friction clutch, which prevents too much tension being applied. This thimble must be rotated through 2 revolutions to open the jaws by 1 mm. In order to measure an object, the object is placed between the jaws and the thimble is rotated using the ratchet until the object is secured. Note that the ratchet knob must be used to secure the object firmly between the jaws. Otherwise, the instrument could be damaged or given an inconsistent reading. The manufacturer recommends 3 clicks of the ratchet before taking the reading. The lock may be used to ensure that the thimble does not rotate while you take the reading. Procedure for micrometer screw gauge. The zero error was determined. The diameter of the ball bearing was measured. Step 2 was repeated 3 times at different positions of the ball bearing. The data was recorded in a suitable table. The actual diameter reading was calculated by taking into consideration the zero obtained earlier. The weight of the ball bearing was determined. The density of the ball bearing was calculated. Next, the procedure for vernier caliper. The whole number or small deviation on the fixed part of the caliper to the left of the zero mark on the vernier was counted. The first mark was found on the vernier that lined up with one of the marks on the part of the caliper. The zero error of the vernier caliper was determined. The length, width, and thickness of the glass block was measured by using the caliper. Step 2 was repeated 3 times at different positions of the glass block. The data was recorded in a suitable table. The actual measurement was calculated by taking into consideration the zero error obtained earlier. The weight of the glass block was determined. The density of the glass block was calculated.
To measure the diameter of ball bearing using the micrometer screw gauge, and for the radius we need to divide the value of diameter by 2. For example, for the first attempt 15.76, we need to divide by 2, and the radius that we got is 7.88. For the glass block, we need to measure the length, width and height. Every measurement must be in 3 attempts. We need to calculate the average of the length, width and height by plus attempt 1, attempt 2 and attempt 3. Then divide it by 3. After measure to the observed reading, we need to measure the true reading. We use the same way to record the true reading, and the data of the true reading has been used to find the density. The formula of density is mass per volume. First of all, we need to calculate the volume. The formula of the volume is V is equal to 4 per 3 multiplied by pi radius cubic, and then replace the value in the formula. Next, for the glass block, the formula of the volume is length multiplied by width and height, and then use the same way, which is replace the value in the formula.
Analysis. Calculate the volume and the uncertainty of the ball bearing and the glass block. The calculation you guys can see in the slide. The volume of ball bearing is 2066.07 and the uncertainty volume is 7.85. Volume of glass block is 1.0969 multiply 10 negative 7 meter cubic, and the uncertainty volume for glass block is 30. The second one is calculate the density and the uncertainty of the ball bearing and the glass block. The calculation you guys can see in the slide. Density of ball bearing is 7792600 kg per meter cubic, and the uncertainty of ball bearing is 0.02. Density of glass block is 2.87 and the uncertainty of glass block is 0.02.
For the discussion, the experiment showed that measurements have same value after being repeated for 3 times. It is important to use the micrometer screw gauge and vernier caliper carefully and correctly to obtain accurate measurement. It is also important to take multiple measurements and calculate the average value to reduce the effect of measurement errors. A micrometer screw gauge is used to measure even smaller objects than the vernier caliper. It consists of a main scale and micrometer scale. The minimum scale is 0.01 mm and the maximum scale is 0.00 mm. Vernier caliper is used to measure the thickness, diameter, length and depth of an object. It consists of the main scale and the vernier scale. The minimum reading is 0.1 cm and the maximum reading is 30 cm. The micrometer screw gauge is used to determine the volume and density of the ball bearing due to its size, which is smaller than the glass block. The vernier caliper is used to determine the volume and density of the glass block due to its size, which is bigger than ball bearing.
Conclusion. The volume of the ball bearing is equals to 2066.07 millimeters cubic. This value depends on the radius of the ball bearing. Its density is equal to 7792600 kilogram per meter cubic. This value depends on the volume and mass of the ball bearing. The glass block's volume equals to 109.69 centimeter cubic. This value depends on the length, width, and height of the glass block. Its density is equals to 2.87. This value depends on the volume and mass of the glass block. Objective of this experiment is to verify the accuracy of Hooke's law. Introduction. If there is a restoring force that is opposing and directly proportional to the distance x that the body is pushed from its equilibrium position, then a body oscillating back and forth is said to be in simple harmonic motion. Disconnecting between the repairing. The equation can be expressed as follows. Force equals to negative K. K is a proportionality constant. The force is always directly toward the equilibrium position and its opposite to the displacement, as shown by the negative sign. When an elastic spring experiences a stretching force of size F, it will stretch from its equilibrium position by a certain amount, x, as determined by Hooke's law. This process will continue until the spring which retracts the spring when it is stretched, equalizes the stretching force. Procedure. The first one is mass of the hanger was measured and recorded. Second one is the weight of the hanger was calculated and recorded as W in the table. Third one is the scale was adjusted so that the pointer on the hanger is near the upper end of the scale. When the hanger is unloaded, the position was recorded as X0. The fourth one is the hanger was loaded by 10 gram mass. The scale reading was recorded. The load have to keep increased by suitable increment. They need to be equal to obtain 8 data points before the lower end of the scale is reached. All data was recorded. The fifth one is the process was reversed by unloading the same load as in 3 against new scale readings for each load was recorded. The sixth one is extension of the spring was calculated. The last step is the extension force acted on the spring for each total load was determined.
The original unit of the started weight is in gram, but the data should be recorded in kilogram. So, we need to change it into kg by divide it with 1000. Mass load can be calculated by plus the mass weight and mass hanger. To find the weight of loaded mass and hanger, we need to multiply the mass load by gravity, which the value is 9.81. Next, the value of extension force is equals to weight of loaded mass and hanger. To find the average of scale reading, we need to plus the trial 1 and trial 2 that have been recorded in the scale reading. Then, divide it by 2. Lastly, to find the extension of the spring, x1 should be minused by x0.
Next, we go to the analysis part. For question number 1, This is a graph of the force causing the extension. Then, the gradient of the graph can be calculated through 2 points that touch a straight line. So, we use the formula y2 minus y1 over x2 minus x1. After that, for question number 2, the work done in stretching the spring through 0.20 meter can be calculated from the graph. Using the formula, F is equals to 1 over 2 multiplied by K and X. Replace the value of K with the gradient and X replace with 2.02 meter that given in the question. Moreover, for question number 3, we use the same formula, but to find the energy value, replace X with X squared. That means the equation will be 1 over 2 multiplied by 2.475 and multiplied by 0.20 square. For question number 4, error that may have occurred during the experiment is human error, such as misreading measurement or incorrect setting up the experiment. Then, error that may have occurred is wind, which make the spring to oscillate. Lastly, arrangement of the apparatus that not following the procedure also may cause the off error. For question number 5, what I can describe from the result is extension of an elastic object such as spring is directly proportional to the force applied to it. For example, value for the first data record on the extension of the spring is 0.009 meter, while the last value is 0.036 meter. By the data result, it shows that the extension of the spring will increase if the force increase.
Based on the result, the average of the scale reading is increased if the mass of the load has been increased. So, because of that, the spring scale has been increased due to mass of the loaded increase. This is able to verify the Hooke law. The Hooke law tells about the force need to extend or compress a spring by some distance is proportional to that distance.
For the conclusion, the objective of this experiment can be verified with the force F and the distance at which the spring is stretched are proportional to each other. That just means linearly dependent on each other, and that the constant of the proportionality is K. By hanging different weight from the spring and measuring the amount of the stretch of the compression, the length of the spring is found to change in length. The spring reading is different from before applying the load.